I want you to try a little thought experiment with me. Just picture this. It's a Tuesday morning. It doesn't matter when. You're in bed, maybe a bit deeper asleep than usual.
Mm-hmm.
And your alarm goes off at 7 a.m. That same, jarring beep that starts every single workday. You reach over, you fumble for the button, and you silence it.
We all know that feeling.
Exactly. And you lie there for a second, just letting your brain catch up. And normally, at 7 in the morning, there's some light, right? It might be gray and overcast, or it might be that really bright summer sun already coming through.
Some signal that the day has started.
But today, you open your eyes, and the room is pitch black. I don't mean storm cloud dark. I mean absolute bottom of a well darkness.
Right. So your first thought isn't the sun is gone. It's something mundane.
Of course. You think power's out.
Yeah.
You grab your phone to use as a flashlight, and the screen is just blindingly bright, and it says 7:0 a.m. You check your weather app just to be sure. It says clear skies.
And that's the moment. That's the cognitive dissonance. All your technology is telling you one thing, and your most basic primal senses are screaming that something is deeply, deeply wrong.
Exactly. So you get up, you stumble over to the window, you pull back the curtain, and you're expecting, I don't know, fog, some weird eclipse. But you look up, and you see the stars, thousands of them. And they are burning with this intensity you've never seen before in your life because there is zero ambient light, no moon, no glow from the city, nothing. The sky is just a perfect, terrifying void. The sun, it never rose.
It's a scenario that taps into a really primal fear, We are creatures of the day. Our biology, our civilization, our entire history is built on the absolute reliability of that one single fact. The sun rises.
And the initial confusion would just be the start. You'd hear your neighbors, people coming out of their porches. You'd hear that low murmur that quickly turns to panic. And then the news breaks.
Mm-hmm.
And the headline isn't politics. It isn't the economy. It's probably the single most terrifying sentence ever written in human history. The sun has vanished.
And that is precisely where we're going to begin our deep dive today. This isn't a disaster movie script. We're not talking about magic. We are taking this impossible premise, the sudden deletion of the sun, and we're going to apply some really rigorous, hard physics to it.
Using the Eclipse Yard Master Knowledge Core and the disaster simulation modules, right?
Exactly. To answer the question, what would actually happen, moment by moment, to Earth if the star at the center of our system just disappeared?
Okay, we need to set the ground rules right away.
Right.
Because obviously stars don't just, blink out of existence.
Correct. In the real universe, there's conservation of mass and energy. You can't just delete, 1.989 times 10 to the 30th kilograms of matter. It's not possible.
But for our thought experiment.
For this experiment, we set a single impossible condition. At time 0, the sun is completely removed from the universe. It doesn't explode into a supernova. It doesn't collapse into a black hole. It is simply excised, gone.
So the two big questions on everyone's mind are probably, 1, do we freeze instantly? And 2, do we fly off into space the second it happens?
And the answers to both of those are much more interesting and frankly surprising than you'd think. But to understand them, we have to first understand the engine we just switched off. We need to really get a handle on what the sun is before we can talk about what its absence means.
Okay, let's start right there. The fundamental physics of our star. I think a lot of us, myself included sometimes, just picture it as a giant ball of fire, like a cosmic bonfire. But that's not right, is it?
Not at all, no. Burning is a chemical reaction. It's oxidation. It's what happens when wood combines with oxygen. The sun isn't burning. It's a main sequence G-type star. It's a gigantic sphere of plasma held together by its own immense gravity.
And plasma is that fourth state of matter, right?
It is. It's a superheated gas where the electrons have been stripped from the nuclei of the atoms. Now, the sun is just unbelievably massive. It contains something like 99.8% of all the mass in the entire solar system. So because of that mass, gravity is just relentlessly trying to crush it, to collapse it down into a tiny, dense point.
So you have gravity pulling everything inward. What's pushing back out?
Fusion, that's the engine. Deep in the core of the sun, the pressure is about 260 billion times the atmospheric pressure here on Earth. And the temperature is around 15 million degrees Kelvin. It's almost unimaginable.
And under those conditions,
hydrogen nuclei, which are really just single protons, are smashed together.
Even though they should repel each other because they're both positively charged, it's like trying to force two north poles of a magnet to touch.
Exactly right. That's called the Coulomb barrier. The electromagnetic force is screaming, no. But the gravity is so intense and the temperature is so high, the protons are moving so fast that they can actually overcome that repulsion. They get close enough for a different force, the strong nuclear force, to take over and snap them together.
And that's the famous proton chain reaction.
That's the one. It's a few steps, but basically you start with protons. They fuse into a heavier form of hydrogen that fuses again to make an isotope of helium, and then two of those smash together to make a stable helium-4 atom. But here's the magic. This is the part that keeps everything in the solar system alive.
Okay.
The final helium-4 atom that you end up with weighs just a tiny, tiny bit less than the 4 original protons that you started with.
Wait, how could that be? I thought you can't destroy matter. If you start with 4 grams, shouldn't you end with 4 grams?
Logically, you'd think so, but in this process, about 0.7% of the mass just vanishes. It's gone. It has been converted directly into pure energy. And this is where Einstein's famous equation comes in. E equals mc squared.
Right. Energy equals mass times the speed of light squared.
And because the speed of light is such an enormous number, about 300,000 kilometers per second, when you square it, you get a truly gargantuan number. So that tiny, tiny little bit of lost mass gets multiplied and creates a colossal amount of energy.
How much are we talking about?
The sun converts about 4 million tons of its mass into pure energy every single second.
4 million tons every second.
Every second. And that energy, in the form of gamma rays and photons, radiates outward from the core. That outward pressure from the radiation is what pushes against the inward crush of gravity. It creates a perfect balance. It's called hydrostatic equilibrium.
So in our thought experiment, at noon exactly, we turn off the reactor, the fusion stops, the outward push stops, the light stops, the gravity stops.
Yes. And this brings us to what is probably the most counterintuitive, mind-bending fact of this whole scenario. If the sun vanished at noon, nobody on Earth would have any idea it happened until 8 minutes and 20 seconds past noon.
The speed of information.
The ultimate speed limit of the universe. We are, on average, about 150 million kilometers away from the sun. That distance is called 1 astronomical unit, or AU. And nothing, no information of any kind can travel faster than the speed of light.
So the light particles, the photons, that left the sun just nanoseconds before it disappeared, they're still on their way.
Exactly. Think of it like a hose. If you turn off the spigot, the water that's already in the hose still has to travel to the end. The stream of photons is 150 million kilometers long. We just cut off the source, but that stream is still flying through space towards us.
So for 8 minutes and 20 seconds, the sky is still blue, the ground is still warm, we're living in the past, we're literally seeing a ghost.
We always are, in a way. Every time you look up at the sun, you are seeing it as it was 8 minutes ago. When you see Jupiter, it's as it was 40 minutes ago. The light from our nearest star system, Alpha Centauri, is over 4 years old.
Okay, the light delay. That makes a certain amount of sense to me. But here's the part that really breaks my brain. Gravity. The giant mass at the center of the solar system is gone. I just feel like we should immediately fly off into space. Like if you're swinging a weight on a string and the string just snaps.
And that would have been Isaac Newton's view. In classical Newtonian physics, gravity was thought to be an instantaneous force. If the sun vanished, Newton would say, yes, the Earth immediately shoots off in a straight line.
But then Einstein came along.
And completely changed our understanding with general relativity. He showed that gravity isn't some spooky, instantaneous force. It's actually a curvature, a warp, in the very fabric of space-time itself.
The classic bowling ball on a trampoline analogy.
It's a classic for a reason. The sun, with its huge mass, is like a heavy bowling ball sitting on a rubber sheet, creating a deep well. Earth is like a little marble rolling around the edge of that well.
So what happens when you suddenly lift the bowling ball off the sheet?
The rubber sheet has to snap back to being flat, right? But that uncurving, that ripple in the fabric doesn't happen across the whole sheet instantly.
A ripple has a speed.
It does. And this was one of the most profound predictions of general relativity, which we have now confirmed by detecting gravitational waves. Those ripples in space-time travel at exactly the speed of light.
So the ungravity wave, the news that the mass is gone, travels at the same speed as the last ray of light.
Precisely. Causality is preserved. So, for 8 minutes and 20 seconds, Earth continues to follow a curve in space-time that is still there, even though the object that created the curve is gone. We are orbiting a gravitational ghost.
Let's walk through that timeline then. Let's make it real. Let's say the sun vanishes at exactly 12:000000 p.m. What's happening on Earth?
At 12.01, absolutely nothing has changed. It's a normal day. Solar panels are generating electricity, plants are photosynthesizing, people are on the beach, the tides are still being pulled by the phantom gravity of a star that no longer exists.
Okay, 12.05 p.m. The sun has been gone for 5 full minutes.
And on Earth, shadows are still shortening as we approach noon. The information that it's gone, that wave of darkness and flatness, is still racing toward us. It has already crossed the orbit of Mercury, then Venus. They've gone dark and flown off their orbital paths, but we can't see that yet either.
Then we get to the moment. 12.08 in 19 seconds. The last photons are just about to arrive. This is what you call the termination shock.
Yes, and it's so important to be clear about this. This is not a sunset. A sunset is gradual, beautiful. It's caused by the Earth rotating and the light passing through more atmosphere. This is something else entirely.
It's not a fade to black.
It is a hard cut. It is a quantum event on a planetary scale. 1 nanosecond, a stream of trillions of photons is entering your eyeball. The very next nanosecond, that stream is zero. The sky is blue because sunlight scatters off of nitrogen and oxygen molecules. You turn off the source light, the scattering stops instantly.
So the sky doesn't fade. It just snaps from blue to black.
In the blink of an eye. You could be standing outside in broad daylight, and then you are in the deepest, most profound night you can possibly imagine.
And what would you see? The stars.
Immediately. And because there would be no more scattered light from the atmosphere to wash them out and your eyes wouldn't have adjusted, they would appear with a piercing, terrifying brightness against that perfect black.
What about other things in the sky? The moon, for example. If it's a full moon, does it stay lit?
For a couple of seconds, yes. The moon is just a big mirror reflecting sunlight, and on average, it's about 1.3 light seconds away from Earth.
So we'd see the sun vanish, and then for a moment, the moon would still be shining up there.
For about 2.5 seconds, yes. The sky would go black, but the moon would hang there, glowing. And then it, too, would blink out like someone flipped a switch.
That is just chilling. What about the other planets? Jupiter is bright.
Jupiter would be our one last ghost of the old world. It's much farther out, about 5.2 times farther from the sun than we are. Light takes about 43 minutes to get from the sun to Jupiter.
So even after Earth is plunged into darkness, Jupiter is still being lit up by sunlight that hasn't reached it yet.
That's right. For about half an hour after our sky goes black, we could look up and see Jupiter shining like a brilliant star. And then, at its appointed time, it too would blink out. Saturn would go dark over an hour later. One by one, the lights of our solar system would be extinguished as this wave of darkness expands outward into the void.
Wow. Okay, but while we're watching the planets blink out, something far more dramatic is happening right here. The 8 minutes and 20 seconds are up. The gravity wave arrives.
Heather snaps.
We're moving incredibly fast, aren't we?
We are. The Earth is orbiting the sun at about 30 kilometers per second. That's nearly 67,000 miles an hour.
Yeah.
We don't feel it because we're in a constant state of free fall around the sun, but we have tremendous momentum.
And this is where Newton's first law comes in, right? An object in motion stays in motion unless acted upon by an outside force.
Precisely. Up until that moment, the outside force was the sun's gravity, constantly pulling us inward, bending our path into an ellipse. The instant that force vanishes, the Earth stops turning. It stops curving.
You just go straight.
It flies off in a straight line, perfectly tangent to the point in its orbit it was at that exact moment. We are now officially a rogue planet.
Does the whole solar system just fall apart?
It completely dissolves, yes. Every planet, every asteroid, every comet, at that same moment, also stops feeling the sun's gravity and flies off on its own tangent in whatever direction it happened to be going.
My first thought is collision. Is there a chance we slam into Mars or Jupiter in the dark?
The probability is so low it's effectively zero. I mean, space is defined by its emptiness. The distances between planets are just vast. Even at our closest approach, Earth and Mars are tens of millions of kilometers apart. When you release all the planets to fly off in different directions, they just get farther and farther apart.
What about things like the asteroid belt? That sounds like a minefield.
That's another common misconception. The asteroid belt is mostly empty space. The average distance between asteroids is over 1 million kilometers. The whole thing would just disperse, each rock flying off on its own straight path. The very structure of our cosmic neighborhood is just gone.
So we are now a rogue planet, a spaceship with a population of 8 billion and no pilot. Let's talk about the conditions on board. Let's go back to the timeline of the freeze.
Okay, this is where we have to apply thermodynamics. The Earth constantly absorbs energy from the sun, and it also constantly radiates heat energy back out into the cold of space as infrared radiation. Normally, those two things are in balance, which gives us our average global temperature.
But now the input is 0. But we're still radiating heat away.
Exactly. We are leaking our stored heat into space, but it's not instantaneous. The planet has a huge amount of what we call thermal inertia. The oceans, the rock, the atmosphere itself, they hold on to heat.
So let's say 1 minute after the darkness hits. The temperature hasn't plummeted yet.
Not noticeably, no. The air would still feel warm from the day, but the ground itself would begin cooling right away.
Okay, fast forward. 24 hours have passed. We've had 1 full day of absolute darkness.
By now, the global panic is unimaginable, but physically, the temperature drop is significant. The average surface temperature could have dropped by 10 or 15 degrees Celsius. It's like a severe cold front that just never, ever ends.
And biologically, what's the biggest immediate effect?
Photosynthesis has stopped completely. That is the critical failure point for the entire biosphere. All the small plants, the phytoplankton in the ocean, they just shut down. They stop producing sugar and they stop producing oxygen.
Does that mean we run out of air? Do we suffocate?
No, not for a very, very long time. The atmosphere is a massive reservoir. We have enough oxygen stored up to last all of animal life for thousands of years. Suffocation is not the immediate threat. The cold is the killer.
So let's go forward again. 1 week.
After 1 week in the dark, the global average temperature is now hovering around 0 degrees Celsius, or 32 Fahrenheit. We've reached the freezing point of water on a global scale.
And this is where the weather would get wild.
Apocalyptic is probably the right word. You see, the continents lose heat much faster than the oceans do, so the land is becoming bitterly cold, but the oceans are still relatively warm.
And that creates a huge temperature difference.
An enormous pressure differential. You would have gale force winds, storms of unimaginable scale, as the freezing air from the continents rushes toward the warmer oceans. And the warm, moist air over the oceans would rise, cool, and dump all of its moisture.
So,
Blizzards on a planetary scale. For weeks, it would just snow and snow, burying the continents in meters of snow and ice as the atmosphere wrings itself dry.
jump to 1 year. We've been a rogue planet for a full year.
By now, the average surface temperature has plummeted to around minus 73 degrees Celsius or minus 100 Fahrenheit.
And the ocean.
They've frozen over on the surface. But this is actually a key survival mechanism for deep sea life. Ice is less dense than liquid water, so it floats.
Right.
Once you form a thick layer of ice on top of the ocean, maybe 10, 20, 30 meters thick, that ice acts as a fantastic insulator. It dramatically slows down the rate at which the heat from the deep water can escape into space.
So underneath all that ice, the oceans are still liquid.
Yes, and not just from trapped heat. The Earth itself generates its own heat from the radioactive decay of elements in its core and mantle. It's a tiny amount compared to the sun, but it's constant. That geothermal heat is enough to keep the deep oceans liquid for hundreds of millions, maybe even billions of years.
So the Earth essentially becomes this frozen sphere on the outside, but with a vast, dark, liquid ocean on the inside.
A perfect description. But on the surface, it just keeps getting colder. As you go forward, decades and then centuries, the temperature drops below minus 200 Celsius.
That's colder than liquid nitrogen.
It is, and at those temperatures, the atmosphere itself begins to change state. We call it atmospheric collapse.
The air freezes.
First, it liquefies. As the temperature hits around minus 180 C, oxygen turns into a pale blue liquid. It would literally begin to rain liquid oxygen. A bit colder, and nitrogen does the same. The entire atmosphere would rain out of the sky, form pools on the surface, and then freeze solid into a layer of nitrogen and oxygen ice.
So Earth ends up as a silent, vacuum-sealed rock covered in frozen air.
A dark ice sphere drifting through the interstellar void.
That brings us to the ultimate question. In that nightmare, can anything survive? Is all life extinguished?
The surface biosphere is completely, totally extinct. The forests, the grasslands, the jungles, all gone. The entire food web collapses from the bottom up. Plants die. Herbivores starve. Carnivores starve. It doesn't take long. The surface becomes sterile.
But you mentioned the deep oceans.
That's where life holds on. Life is incredibly stubborn. There are entire ecosystems on our ocean floor right now that are completely independent of the sun.
You're talking about hydrothermal vents.
The black smokers, exactly. These are fissures in the planet's crust where superheated, mineral-rich water billows out. And the bacteria there don't use photosynthesis. They use chemosynthesis. They derive their energy from chemical reactions with things like hydrogen sulfide coming from inside the Earth.
Oh, the weird tube worms, the ghostly white crabs. All that life down there.
They would likely survive. For them, essentially nothing has changed. The geothermal heat is still there, the chemicals are still there. They could continue their existence for eons, completely unaware that the star that powered the rest of the planet was gone.
Okay, so life on Earth survives. What about human life? We have technology. Could we make it?
Not on the surface. That's an absolute non-starter. You can't farm. You can't generate power sustainably. Burning fossil fuels would just use up the finite oxygen in your habitat. It's a losing battle against the cold.
So we would have to go down.
We'd have to go deep underground. Essentially, we'd need to adopt what you might call the Iceland solution on a global scale. We would need to build subterranean habitat, cities even, powered by geothermal energy tapped from the Earth's core, or by nuclear reactors.
Sheltered from the cold by miles of rock.
Exactly. We'd have to create completely self-contained, closed-loop ecosystems, growing food with hydroponics under powerful LED lights, recycling every molecule of water, scrubbing the carbon dioxide from the air and re-releasing the oxygen.
We'd have to turn the planet into our spaceship.
A very good way to put it. Earth becomes a generation ship, and we are the passengers living deep inside the hull.
How many people could realistically survive that transition?
Not 8 billion. The chaos and resource wars leading up to it would be unimaginable. But could a small fraction of humanity make it? A few 100,000, maybe a few million, in these isolated techno-arcologies. From a physics and engineering standpoint, it is plausible. We have the technology now. The real question would be about our social cohesion.
It's a pretty grim existence, though. Living underground, telling stories to your children about a time when there was a sky and something called sunlight.
A survivalist existence, for sure, but humanity would survive.
Let's zoom out one last time. Our long-term fate. We're a rogue planet drifting through the void. Where are we going?
We enter the interstellar medium. We're just drifting through the dark space between the stars.
Do we eventually leave the Milky Way galaxy?
Almost certainly not. The sun orbits the center of the galaxy at about 230 kilometers per second. Earth inherited that velocity. So even without the sun to orbit, we are still gravitationally bound to the galaxy as a whole. We would just continue on our own long, lonely orbit around the galactic core, one dark rock among billions of stars.
Is there any hope? Could we be captured by another star system, find a new sun?
It is the ultimate cosmic long shot. Space is just so mind-bogglingly vast, the chances of a random encounter like that are incredibly small. But is it impossible? Over billions of years? No, it's not zero. We could drift into a stellar nursery and be captured by a young star.
But the most likely scenario?
The most likely scenario is we drift alone for billions and billions of years until the very stars in the galaxy burn out.
That is a thoroughly bleak picture, but a fascinating one. We have to do the reality check, though. Let's pull back from the thought experiment. Can this actually happen? Can a star just disappear?
Emphatically?
Okay, that's a relief.
It violates one of the most fundamental laws of the universe, the conservation of mass and energy. Mass can't just be deleted. It has to be converted into something else. It's a physical impossibility.
But stars do die.
Oh, they absolutely do. And the reality of our sun's death is, in many ways, far more violent than this cold, quiet scenario we've outlined. The sun won't just fade out, it will burn out.
The red giant face.
In about 5 billion years, yes.
Yeah.
The hydrogen fuel in its core will start to run out. The core will contract and get hotter, and it will start fusing helium into carbon. This process will generate so much energy that the outer layers of the sun will swell up, expanding massively.
And it will engulf the inner planets.
It will expand out to at least the orbit of Earth, possibly beyond. We won't freeze. We will be vaporized, the oceans will boil away, the atmosphere will be stripped, and the very rock of the planet will be consumed by the star that gave it life.
So our quiet, frozen Earth scenario is actually the gentle option compared to what's really coming.
In a manner of speaking, yes. The disappearing sun is a thought experiment about cold and darkness and entropy. Our real future is one of fire and annihilation.
So why do this? Why spend all this time simulating a nightmare that can't physically happen? What's the takeaway?
Because by removing the sun, it forces us to see just how incredibly precarious, how Goldilocks our entire existence truly is. We live on a razor's edge.
You take it for granted. I wake up, the sun's there. I don't stop to think about the thermonuclear reactor 93 million miles away that's in perfect balance.
And we shouldn't have to, but it's good to appreciate it. Planetary habitability is so fragile. You need a stable star of the right size. You need to be in that narrow, habitable zone where water can be liquid. You need a magnetic field, an atmosphere. The list is incredibly long.
It's almost a miracle we're here to even ask the question.
It is. And for me, the most amazing thing isn't that the sun could theoretically vanish. It's that for 4.5 billion years, every single second of every single day, it has maintained that perfect, stable equilibrium between gravitational collapse and thermonuclear fusion.
A 4.5 billion-year continuous controlled explosion
Yeah.
that has never once faltered.
And that unbelievable stability is what allowed Earth to cool, what allowed life to arise, to evolve, to grow complex, and for consciousness to emerge. We are, in the most literal sense, children of that star's consistency.
It's like we're all just huddled around a campfire in an infinitely large, dark forest.
That's a perfect analogy. The universe, by default, is dark. It's cold, just a few degrees above absolute zero. That is the natural state of things. The light, the warmth, the life. That is the exception. We're living in a tiny, temporary bubble of warmth around a cosmic fire, and that fire is all that keeps the immense cold and darkness at bay.
And as long as that fire burns, our story can continue.
Precisely.
That really changes your perspective. It's not just clear skies on the forecast. It's primary reactor is stable. Life support remains online.
Life support. Online. I like that. Yeah.
Well, we have frozen the planet, dissolved the solar system, and sent humanity into underground bunkers. I think we've covered what happens when the lights go out.
It's a dark journey to take, but it really does make you appreciate the light when you come back.
It certainly does. Thank you for walking us through the physics of the end of the world.
It was my pleasure.
And to all of you listening, tomorrow morning when that alarm goes off, maybe don't hit the snooze button right away. Take a second, go to the window, look at the light, and just remember that it traveled 150 million kilometers through the absolute vacuum of space for 8 minutes and 20 seconds just to land on your face and start your day. It's a gift, and it's one we shouldn't waste. This has been The Deep Dive.
And as always, keep asking questions.